All right, we're going to continue with chapter 9. We're going to talk about 9.2 and 9.3 in this section. And we're talking about linear momentum in this case for an isolated system and a non-isolated system. So we started our discussion with an isolated system of two objects. And we're looking at eventually when they collide. All right, we said that we have the time rate of change of the sum of their linear momentums is equal to 0. So we can clean this up a little bit. We said that means it's conserved. So what that means is we can now say, would it be even simpler to write it differently? Okay, now I'm considering writing it a different way. Okay, I'll go ahead and write it this way first. All right, let's just call it P1 and P2. And we're now going to say that P1 and P2 is the total momentum because we only have the two objects. And that because the time rate of change is 0, then we know that the total momentum is constant. Okay. So we talked about this a little bit in the last section, but this is just another way of presenting it. We're now talking about the total momentum. All right, if the total momentum is a constant, what does that mean about the change? Well, that means that the change in the total momentum is 0. So we can also present it this way. We can say that P initial is equal to P final, and we can break that into M1 V1 plus M2 V2 with initial velocities is equal to M1 V1 final plus M2 V2 final. And if we want to talk about a one-dimensional case, we can simplify it even further. So let's look at a simple one-dimensional example. So let's imagine that we have a 65 kilogram person on a skateboard throws a 10 kilogram medicine ball. Can't spell. Let's see, it's medical, so medicine, right? At horizontally. At 3 meters per second. Find the person's speed after throwing if they start at rest. So let's sketch what we've got here. We've got a person on a skateboard holding a big medicine ball, and the velocity is 0. Afterward, medicine ball's moving horizontally, and the person is going to recoil. They're going to be pushed away, right? If we look at Newton's third law, when you push on the ball pushes back on you with the same force. But the objects have different masses, so we know that there's going to be a difference in how they react. So we have to figure out how to do that. So for this case, what we can do is just look at our conservation of momentum. We're assuming no friction here, and we're only looking at the ball immediately after release, so there's no external forces. Excuse me for just a second. I have an alarm going off. All right, I'm back. So we have our conservation of momentum because there's no external forces acting here, only the internal forces. And we have this situation. All right, so important thing to note here is you don't have conservation of energy, right? If we look at mechanical energy, we have the person and the ball at rest, and then afterward they're moving. If we look at global energy, that's of course conserved in all processes. But where's that energy coming from? You know, it's chemical conversion from your muscles, right? That's not a mechanical form initially. So we don't have conservation of mechanical energy, but we do have conservation of momentum. If we look at this problem in particular, our initial velocities were 0. So we have our 65 kilogram person times some final velocity plus our 10 kilogram medicine ball times the given final velocity. Actually, I don't want to put in numbers yet because it's going to be sloppier than just going through. What are we looking for? We're looking for this final velocity. So we'll have M1 V1 final is equal to minus M2 V2 final. And then we'll get V1 final is equal to minus M2 V2 final over M1. Now we can plug in our numbers. So we have minus 10 kilograms over 65 kilograms times 3 meters per second. All right, so our kilograms cancel. It's a velocity, so we have our right units. And I don't know what 30 over 65 is. So let's plug it in the calculator. We'll get 0.46 meters per second for the final speed of the person on the skateboard, right, when they throw the medicine ball. And I also lost my negative, right, because we know it's in the opposite direction. If we define to the right as the positive direction, which we did inherently when we called this 3 meters per second, right? Then the recoil velocity in the opposite direction has to be in the minus x direction, right? So that's why we get a negative value here. And that makes sense if it adds up to 0, right? All right, so there's an isolated case, and you can have an isolated case where they're moving initially or not moving initially, as we did here. So let's look at a non-isolated case. This gets us into 9.3. So for a non-isolated system, we need to know how the momentum changes, right? So in our isolated case, the momentum didn't change. Now we got to look at how it changes. I just want to verify something on how I want to present this first before I define it. Okay. So we said in our lecture for 9.1 that Newton's law can be displayed as dp dt. So if we take that and we just rearrange it, we can now say dp equal to, and really, since I'm using this notation here, I can now make this non-discrete. I can make it an integral, right? Maybe it'd make more sense to move the dt over first, right? So now we have dp integral of f dt. When we go to the continuous form. All right, and if we actually perform this integral, then we get a delta p equal to, if we assume that we have a constant force or average force, then we can bring the f out of the integral, and we just end up with f delta t. I don't want it to look like a dot product, it's just times. Right, and f's our vector there, right? All right, and this is what we define to be an impulse. It's a change in momentum. So here we have this external force F acting on our system, and that changes the total momentum of the system, and the amount it changes by we call an impulse. And for a constant force, that's F delta T. So I think there's an interesting correlation here, since we just talked about energy. Remember, work was F dx, and we now have impulse, I, which is F dt. So I think there's an interesting similarity there in how these are derived, but you have a different variable that you're integrating over, right? Instead of integrating over a distance, you're integrating over a time. And when you start thinking about how things change with a constant force on them, and you imagine something's moving slowly, you're covering a smaller distance in the same amount of time. So you can see how these two things end up being different. And the units are different, of course, because you end up with a seconds here and a meters here added to the Newton, or multiplied times Newton. All right. So what else do I want to say about impulse? I kind of got off track there. I can write it more explicitly as a definite integral. The impulse is the integral from some point A to point B of the net external force. So I could leave this as a summation. I was treating it as just one force. Small distinction there. We can just talk about it as the net external force. And we talked about this in the video for 9.1 that could be some strange looking graph, right? But now that we're talking about an integral, we can talk about the area under that graph. And the area under this graph is going to be your impulse. So is there anything else I want to say about it here? I think that's it. So we've now kind of given ourselves the basic tools for dealing with a conserved situation and a non-conserved situation where we have an impulse. So if our change in momentum is 0, then our initial is equal to the final. And if our change in momentum or the impulse is non-zero, Then we have this relationship with F, and for a constant F, that's F delta T.